The universe is expanding. Across the sky, distant galaxies show a pattern that is impossible to ignore. On the largest scales, the farther away a galaxy is, the faster the distance between us and that galaxy is growing. But if the universe is growing, what is it growing into? A balloon expands into the room around it. A fireball expands into the air. Every expanding thing we know seems to need somewhere larger to go. The universe may not. It has no known spatial center. The observable universe has a horizon, but that horizon is not a wall. And in our best theory of gravity, cosmic expansion can be described completely without placing the universe inside any larger space. So the answer is not simply nothing, and it is not secretly empty space. The real answer is stranger, more precise, and far more honest. To reach it, we first have to understand what astronomers actually mean when they say the universe is expanding. Everything is moving away. The story begins with light. When astronomers spread the light of a star or galaxy into a spectrum, they see narrow lines produced by atoms such as hydrogen, helium, and calcium. In the laboratory, those lines appear at known wavelengths. In the sky, the same patterns can shift. Beginning in the early 20th century, the American astronomer Vesto Slipher measured the spectra of objects then called spiral nebulae. Most showed shifts toward longer, redder wavelengths. Interpreted as radial motion, the measurements suggested that many of these systems were receding at remarkable speeds. Redshift needs a little care. Nearby motion can shift light through the familiar Doppler effect, much as the pitch of a passing siren changes. Across cosmological distances, however, the dominant effect is different. While the light travels, the large-scale geometry of the universe changes, increasing the wavelength of the light. That is cosmological redshift. While observers were collecting spectra, theorists were discovering that Einstein's equations did not naturally prefer a static universe. In 1922, the Russian mathematician Alexander Friedmann published solutions in which the cosmic scale could change with time. In 1927, the Belgian physicist and priest Georges Lemaître independently developed an expanding model and derived a relation between distance and recession speed. Several years later, in 1931, he proposed his more famous primeval atom idea, an early attempt to describe a cosmic beginning. Then came Edwin Hubble. In 1929, Hubble combined estimated galaxy distances with recession velocities, many based on Slipher's measurements, and published the now-famous distance velocity pattern. Lemaître had already derived and estimated the relation theoretically and observationally, which is why it is now officially called the Hubble-Lemaître law. The early numerical value was badly wrong because the galaxy distance scale was still young. That did not erase the pattern. Later observations corrected the distances and transformed the constant into one of the central measured parameters of cosmology, the Hubble parameter, which changes with cosmic time. Its present value is called the Hubble constant. At sufficiently modest redshifts and on scales large enough for local motions to average out, the rule is approximately linear, double the distance, and the recession rate is about twice as large. The modern relation is written as velocity equals the Hubble parameter multiplied by distance. At greater distances, the simple linear formula must be used with care because the Hubble parameter evolves and redshift no longer converts to a unique ordinary velocity through the elementary Doppler equation. Cosmologists instead fit a full expansion history. The pattern does not mean that Earth occupies the middle of an explosion. In a homogeneous expansion, every widely separated observer sees the same basic relation. More distance means more expanding space between the observer and the galaxy, so the total rate at which their separation grows is larger. A useful mental image is a long elastic strip marked with dots. Stretch the strip uniformly. Every dot becomes farther from every other dot, and widely separated pairs gain distance faster because more of the strip lies between them. The dots also have their own small motions, but the large-scale pattern comes from the changing separation. Real galaxies have those additional motions, called peculiar velocities. Gravity can pull neighbors together even while the universe expands on larger scales. Andromeda, about 2.5 million light-years away, is blue-shifted and approaching the Milky Way at roughly 100 kilometers per second along our line of sight. That does not prove cosmic expansion has stopped nearby. It shows that the local group is gravitationally bound, so local gravity dominates over the large-scale Hubble flow. The future orbit of the Milky Way and Andromeda is still being refined. Recent analyses do not agree on whether a full merger is inevitable. The lesson is simple. Cosmic expansion is a large-scale pattern, not a force that drags apart every object. Galaxies can approach, orbit, and collide locally. Across the great distances between unbound galaxy groups, however, the expansion becomes unmistakable. And once we understand that pattern, a familiar picture begins to fall apart. The Big Bang was not debris exploding outward from one location into a pre-existing emptiness. The Big Bang did not happen at one place. Say the words Big Bang, and it is natural to picture a tiny glowing point suspended in darkness. Then it detonates, throwing matter into empty space. That image is vivid, but it is not the modern cosmological model. The Big Bang was not an explosion at one place in space. It describes an early era when the observable universe was far hotter, denser, and more uniform, and when the large-scale distances between what would later become galaxies were much smaller. If we follow the expansion backward, the scale factor decreases. Matter and radiation become denser. Temperatures rise. Our equations eventually reach conditions so extreme that a complete theory of quantum gravity would be needed. The model does not give us a reliable movie of an ordinary object exploding at time zero. There is no known central blast site to point toward. In the standard homogeneous model, the early hot dense state existed throughout space. Every co-moving region we observe today traces back to that early state. The Big Bang is better understood as a chapter in cosmic time than as a location on a cosmic map. This also explains why observers in distant galaxies would see the same overall expansion pattern. Each observer sees remote, unbound galaxies receding in all directions after local motions are averaged out. That does not place each observer at a physical center. It means the large-scale universe has no preferred location in the model. Cosmologists often express this through the cosmological principle. On sufficiently large scales, the universe is approximately homogeneous and isotropic. Homogeneous means no large region is fundamentally privileged over another. Isotropic means the statistical view is approximately the same in every direction. The balloon analogy captures part of this idea. Imagine dots drawn on the two-dimensional surface of a balloon. As the surface expands, every dot becomes farther from every other dot. No dot on the surface is the center of the expansion, and more widely separated dots move apart faster. But the analogy carries a trap. A real balloon has a center inside it and a room outside it. Those features are not part of the cosmological lesson. The balloon's surface represents all the spatial directions available to the imagined two-dimensional inhabitants. The air inside the balloon is not evidence for a real exterior dimension surrounding our universe. Raisin bread offers another partial picture. As dough rises, the raisins separate, and distant raisins separate more quickly. But real bread has an edge, an oven, and air around it. Those are properties of bread, not conclusions about the universe. Even the phrase, "space itself expands," is an analogy if taken too literally. General relativity does not describe space as a material fabric with molecules being pulled. It describes space-time geometry and how distances between co-moving locations change. So keep the useful parts of the analogies. No preferred spatial center, uniform large-scale expansion, and a distance-dependent recession rate. Discard the accidental parts, a surrounding room, a central point in a higher dimension, and a visible outer surface. There is another subtlety. The universe has a finite age, but that does not mean all of space began as one mathematical point. If the complete universe is infinite today, it could also have been infinite at earlier times, only much denser, with every large-scale separation reduced by the same scale factor. The Big Bang did not necessarily turn nothing into an expanding ball. It tells us that the universe evolved from a much hotter and denser state. Evidence for that history includes the expansion itself, the cosmic microwave background, and the observed abundances of light elements forged during the first minutes. Those independent clues all point toward a hot, early universe, even though they do not by themselves explain an absolute beginning. Questions about an absolute beginning, or why there is something rather than nothing, extend beyond what the standard Big Bang model by itself can answer. But even without a central explosion, perhaps the universe still has an outer edge. Perhaps our telescopes simply have not reached it yet. To understand why that idea is also misleading, we have to separate the whole universe from the part of it we can observe. Does the universe have an edge? Looking into space is also looking into the past. Sunlight takes a little over 8 minutes to reach Earth. Light from Proxima Centauri takes more than 4 years. The light we see from Andromeda began its journey about 2.5 million years ago. The deeper we look, the younger the universe appears. Because the universe is about 13.8 billion years old and light travels at a finite speed, there is a limit to how far information could have reached us. That causal limit is associated with the particle horizon and defines the observable universe. The word observable does not mean visible with today's telescope. It means, in principle, capable of having influenced us since the early universe. Better telescopes can reveal fainter objects within that region, but they cannot make signals arrive from beyond the particle horizon. This horizon is not a physical shell floating in space. It is not a wall, and there is no reason to expect a sign saying the universe ends here. Every observer has an observable region centered on their own location, just as every person standing in fog has a horizon centered on themselves. Now comes one of cosmology's most surprising numbers. The universe is about 13.8 billion years old, yet the present co-moving radius of the observable universe is roughly 46 billion light years. Its diameter is about 93 billion light years. The reason is that the universe expanded while the light was traveling. The oldest signals did not cross a static distance of 46 billion light years. They began much closer to the matter that would eventually become us, while the large-scale separation grew during the journey. The 46 billion light-year figure describes where that ancient matter is estimated to be now in co-moving coordinates, not how many years the photons traveled. To feel the scale, begin with Earth, about 13,000 kilometers wide. Light crosses it in a fraction of a second. The distance from Earth to the Sun is about 8 light minutes. The outer planets lie light hours away. The nearest star beyond the Sun is more than 4 light years away. The Oort cloud, if it extends as far as many models suggest, may reach a substantial fraction of the way to the nearest stars. That alone shows how quickly familiar scales stop feeling intuitive. The Milky Way spans roughly 100,000 light years. The local group, containing the Milky Way, Andromeda, and many smaller galaxies, extends across roughly 10 million light years. Beyond it, galaxy groups and clusters form filaments, walls, and voids. The region mapped as Laniakea stretches across hundreds of millions of light years, although it is a flow-defined supercluster region, not one single gravitationally bound object. And all of that is tiny beside the observable universe, about 93 billion light years from one side of our current horizon to the other. The visible cosmic web is not the whole universe. It is the portion from which information has had time to reach us. Does space continue beyond that horizon? We cannot directly observe it, but the standard model does not predict a wall there, and the large-scale smoothness we observe is consistent with more universe beyond our view. Most cosmologists expect our observable region to be only part of a larger whole, although the total size cannot presently be measured. The complete universe could be infinite. If so, there is no outer boundary because space continues without end. Or it could be finite yet unbounded. A sphere's surface provides a two-dimensional example of finite but unbounded geometry. The surface has a finite area, yet a traveler can move along it without encountering an edge. In an idealized closed three-dimensional space, a sufficiently long path could in principle return to its starting region without crossing a boundary. But curvature and total size are not the same question. Positive spatial curvature is analogous to a sphere. Negative curvature is often compared with a saddle. Zero curvature is called spatially flat, meaning Euclidean geometry works on large scales. Yet topology determines how space is globally connected. A flat space can be infinite, but it can also be finite if directions wrap around, as in a three-dimensional torus. Negatively curved spaces can also have finite topologies. That is why measuring curvature does not automatically reveal whether the universe is finite or infinite. Combined observations, especially the cosmic microwave background together with baryon acoustic oscillation measurements, are consistent with spatial curvature extremely close to zero within the standard model. That tells us our observable region is very nearly flat. It does not prove the entire universe is infinite, and it does not reveal the global topology. The observable universe also changes with time. As new light reaches us, the particle horizon grows in co-moving distance, while accelerated expansion creates a separate event horizon that limits which new signals will ever arrive. The phrase, "the edge of the observable universe," therefore describes causal history, not a fixed border painted onto space. Searches for repeating patterns in the cosmic microwave background have not produced convincing evidence that space wraps around on a scale smaller than the observable universe. So if the universe is finite in that way, its repeating scale must be large enough to have escaped detection. We therefore know the location of our observational horizon, but we do not know the total extent or global connectedness of space. The edge of the observable universe is the edge of our information, not a confirmed edge of existence. And that brings us back to the question at the center of this documentary. If there is no known wall moving outward, what exactly is changing when the universe expands? So what is it expanding into? In everyday life, size is measured inside a surrounding space. A balloon gets larger relative to the room. A cloud expands through the atmosphere. That intuition makes the universe seem as if it must be an object inside something bigger. General relativity does not require that picture. Cosmologists model the large-scale universe with a space-time metric. A metric is the mathematical rule for measuring intervals. How much distance lies between locations and how much time separates events. In an expanding cosmological solution, the large-scale spatial part of that rule changes with cosmic time. The change is summarized by the scale factor. By convention, we can set today's scale factor to 1. At an earlier time, if the scale factor was 1/2, the proper distance between two widely separated co-moving locations was half its present value. This statement applies to the large-scale cosmic flow, not to bound objects such as atoms, planets, solar systems, or galaxies. The same mathematics works whether the spatial sections are infinite or finite. In an infinite model, every large-scale separation can grow while the space remains infinite. In a finite, unbounded model, the total spatial volume can grow without acquiring a boundary. The universe does not need an exterior volume for those internal distances to change. General relativity can describe a complete space-time using relationships measured entirely from within it. An ant living on an abstract curved surface can define distances and curvature without referring to a surrounding three-dimensional room. In the same way, cosmic geometry can be intrinsic. Does expansion happen everywhere? The scale factor belongs to the idealized large-scale cosmological model. It is meaningful after matter is averaged over enormous distances. A galaxy, a solar system, or a laboratory is described by local space-time and binding forces, not by placing a tiny Hubble expansion inside every ruler. People sometimes say that expansion creates new space. That can be a useful shortcut, but it should not be mistaken for a microscopic process producing chunks of substance. The precise statement is that the metric scale factor increases, so the proper distance between co-moving, unbound regions grows. General relativity does not supply a universal counter that counts newly manufactured units of space. Another analogy asks, what is north of the North Pole? On Earth's surface, north is a direction defined within the surface, and the question stops being defined at the pole. In a similar spirit, outside all space may fail to describe a location within the theory, but the analogy has limits. The North Pole exists inside a larger three-dimensional world, and the universe might have physics beyond our current models. The analogy shows how a question can contain a hidden assumption. It does not prove that no larger reality exists. This is where four statements must be separated. First, an outside is not required. Standard general relativity describes cosmic expansion without embedding the universe in a pre-existing external space. Second, an outside is not defined by the model. If the universe means the totality of physical space-time, then outside space-time is not another coordinate the equations automatically provide. Third, a larger reality is unknown. The observable universe is limited, and current experiments cannot survey an exterior to all space-time. Some speculative theories contain extra dimensions or broader structures, but those ideas are not necessary to explain the observed expansion. Fourth, an outside has not been proven impossible. Science should not turn the limits of a model into a claim of absolute non-existence. So what is the universe expanding into? The clearest answer is this. In standard cosmology, it is not modeled as expanding into anything. Expansion means that large-scale distances within the universe increase as the metric evolves. No physical outer boundary has to move through a surrounding void. If the universe is infinite, expansion increases distances within an already infinite space. Infinity does not become more infinite. The density and separations change. If the universe is finite and unbounded, its total spatial volume can increase without an edge pushing outward into anything. Could the universe nevertheless be embedded in a higher dimensional space? Some mathematical and speculative physical theories allow such constructions, but no confirmed observation requires them for ordinary cosmic expansion, and the balloon analogy is not evidence that they are real. This answer can feel like a refusal because human intuition was built for objects inside environments. Cosmology asks us to treat the geometry itself as dynamic. The universe may not be a thing moving through space. It may be the space whose internal relationships are changing. But the expansion is not merely continuing. During the last several billion years, it has been accelerating. Understanding that discovery reveals both what we know about the universe and how much remains hidden. Dark energy and the accelerating universe. For much of the 20th century, cosmologists expected gravity to slow the expansion. Matter attracts matter, so the average cosmic expansion rate should have been decelerating, even if it never reversed. In the 1990s, two independent teams tested that expectation using distant Type 1a supernovae. These thermonuclear explosions are not perfectly identical, but their light curves and colors can be standardized, allowing astronomers to infer their relative luminosities and distances. The teams found that distant supernova appeared dimmer than expected in a decelerating universe. The best interpretation was astonishing. Cosmic expansion had transitioned from slowing to accelerating. The discovery was announced in 1998 and 1999, and the leaders of the two teams later shared the 2011 Nobel Prize in Physics. Dark energy is the name given to the component or effect associated with that acceleration. The name does not identify a known substance. It marks a gap in understanding. There is another wording trap here. Accelerating expansion means the scale factor has positive acceleration in the cosmological model. It does not mean every individual galaxy's measured recession speed must increase in a simple way at every moment, because recession depends on both distance and the changing Hubble parameter. Within the standard lambda cold dark matter model, roughly 2/3 of today's cosmic energy density behaves like dark energy, while the remainder is mostly dark matter and ordinary matter. The exact fractions depend on the dataset and model, so about 68% is a better description than a timeless exact number. The simplest model is Einstein's cosmological constant, written with the Greek letter lambda. In that model, the vacuum has a constant energy density and negative pressure. As matter and radiation dilute while the universe expands, the vacuum component does not dilute in the same way. It therefore becomes increasingly dominant, allowing the expansion to accelerate. It is misleading to say that a constant dark energy grows stronger because more space exists. Its density remains constant in the lambda model. What changes is the balance. Matter becomes more dilute, while the cosmological constant remains. The model fits a wide range of observations remarkably well, but its physical origin is unknown. Quantum field theory suggests that vacuum fluctuations should contribute energy, yet simple estimates disagree catastrophically with the tiny observed cosmological value. Depending on assumptions, the mismatch can span an enormous number of orders of magnitude. This cosmological constant problem is one of the deepest unsolved puzzles in physics. Dark energy might also be dynamical rather than constant. To test that possibility, astronomers measure the expansion history with supernovae, the cosmic microwave background, gravitational lensing, and baryon acoustic oscillations, a preferred scale in the clustering of matter that acts as a cosmic standard ruler. The Dark Energy Spectroscopic Instrument, or DESI, was built for this work. Mounted on the Mayall telescope in Arizona, it uses thousands of fibers to collect spectra from many objects at once. By April 2026, DESI had completed the observations planned for its original 5-year map, measuring more than 47 million galaxies and quasars while continuing an extended survey. DSI reconstructs cosmic history by measuring redshifts and the baryon acoustic oscillation scale at different epochs. That standard ruler does not determine dark energy alone. Its power comes from combining distance and expansion information with other observations. The most recent published cosmological analysis available from DESY's first 3 years used nearly 15 million well-measured galaxies and quasars. DESI's data by themselves remain consistent with the standard lambda model. When combined with selected cosmic microwave background, supernova, weak lensing, and other datasets, some combinations prefer evolving dark energy at about 2.8 to 4.2 sigma. That is intriguing, but it is below the 5 sigma convention usually associated with a discovery, and different combinations give different strengths. The collaboration describes the result as a strengthening hint, not proof. Results from the completed 5-year dataset are expected to provide a much sharper test. A separate modern puzzle concerns the numerical value of today's expansion rate. Measurements calibrated from the nearby universe often give a higher Hubble constant than values inferred from the early universe under the standard model. This Hubble tension could reflect hidden systematics or missing physics, and it remains unresolved. It does not tell us what the universe expands into, but it reminds us that even the expansion rate is still being investigated. Acceleration does not mean that everything is expanding internally. The standard cosmological metric is a large-scale description. Regions that have collapsed and become gravitationally bound do not simply follow the Hubble flow. Electromagnetic forces bind atoms and solid objects. Gravity binds planets, star systems, galaxies, and galaxy groups. That is why Earth does not grow. The distance from Earth to the Sun does not increase according to the Hubble law, and the Milky Way is not being stretched apart. On the largest unbound scales, expansion dominates. Inside stable bound systems, local dynamics dominate. Cosmic expansion also allows recession rates greater than the speed of light. This does not mean a galaxy passes a nearby observer faster than light. Special relativity limits local motion through spacetime. Cosmological recession is a rate of change of proper distance across a large, curved, evolving spacetime. Adding the expansion across enough intervening distance can produce a recession rate above light speed, without any local violation. 3 distance scales are often confused here. The Hubble radius is the distance at which the present recession rate equals the speed of light. It is a useful scale, but it is not generally a true one-way horizon. Light emitted beyond the Hubble radius can, in some cosmological histories, later cross inside it and reach us. The particle horizon is the greatest co-moving distance from which signals could have reached us since the early universe. it sets the present boundary of the observable universe. The cosmic event horizon asks a different question. How far away can an event occur now and still ever send a signal that reaches us in the future? In an eternally accelerating lambda-like universe, there are regions whose light emitted today will never arrive, even over infinite time. These horizons are not material surfaces. A galaxy does not smash into one. They are causal boundaries determined by the expansion history. The distinction matters because a galaxy can be visible today, even if it is currently receding faster than light, and even if signals it emits today will never reach us. We see ancient light that began its journey when conditions and distances were different. So acceleration changes more than a number on a graph. It determines which parts of the universe can ever communicate with us and what the night sky will look like in the remote future. To understand how much may already lie beyond our reach, we have to return to the earliest moments we can meaningfully model. The universe beyond our reach. The observable universe may be enormous, but it is not necessarily a representative measure of the full cosmic extent. One leading idea about the very early universe is cosmic inflation, a brief period during which the scale factor increased extraordinarily rapidly. Inflation was developed to explain why widely separated regions have nearly the same temperature, why observable space is so close to flat, and why unwanted relics predicted by some early particle theories are not seen. Inflation is not observed directly as a filmed event. It is a theoretical framework whose broad predictions are compatible with important features of the cosmic microwave background, including nearly scale invariant, predominantly adiabatic primordial fluctuations. Many specific inflation models have been ruled out or constrained, and the physical mechanism remains unknown. A key observational target is a primordial background of gravitational waves, which some inflation models predict would leave a distinctive pattern in cosmic microwave background polarization. That signature has not been securely detected. Its absence does not eliminate inflation, but it rules out or pressures some of the simplest high-energy models. If inflation occurred, the region that became our observable universe may have originated from a tiny, causally connected patch that was stretched to cosmic size. The full inflated region could be vastly larger than what we can observe. This is one reason cosmologists take seriously the possibility that much more universe exists beyond our particle horizon. The cosmic microwave background gives us our earliest direct electromagnetic image. It was released when the universe became transparent, roughly 380,000 years after the hot Big Bang. Missions such as WMAP and Planck mapped its temperature and polarization patterns with extraordinary precision. The characteristic angular scale of the microwave background's acoustic pattern acts as a geometric test. But the cosmic microwave background alone can trade curvature against other parameters. Combining it with baryon acoustic oscillation measurements breaks much of that degeneracy. Together, they constrain spatial curvature to be extremely close to zero under standard cosmological assumptions. Planck analyses combined with BAO found consistency with flatness at about the sub-percent level. Near flatness does not prove infinity. A flat universe can have a compact topology, and a slightly curved universe can be far larger than our observable region. The measurements tell us that any radius of curvature is very large compared with the portion we can see, not that the full universe has been mapped. Inflation also opens a more speculative door. In some models, inflation ends in regions like ours while continuing elsewhere. This is called eternal inflation. It can produce many expanding regions, sometimes described as bubble universes. and it is often connected with multiverse proposals. These ideas are not direct observations. They depend on particular models and may be extremely difficult, perhaps impossible to test decisively. They should be presented as theoretical possibilities, not established cosmic geography. The future depends on the nature of dark energy. A true cosmological constant leads toward an increasingly cold and isolated universe. A component that weakens could change that forecast, and a component that grows in density could lead to more extreme endings. The current data are not sufficient to choose among every possible model. The distant future is less speculative if dark energy remains close to a cosmological constant. Galaxies outside our gravitationally bound neighborhood will continue to recede. Their light will become increasingly redshifted and faint. Over immense timescales, more of them will pass beyond our event horizon, so no signal emitted after that crossing can ever reach us. A far future civilization could inhabit a sky in which the wider cosmic expansion is almost impossible to discover. Its local merged or rearranged galaxies would remain, but most distant galaxies would have faded beyond detection. The cosmic microwave background would be stretched to wavelengths increasingly difficult to observe. The local group is gravitationally bound and will not be pulled apart by the ordinary acceleration described by lambda cold dark matter. The Milky Way and Andromeda are approaching, but their exact long-term encounter is no longer considered certain. Recent simulations using updated measurements find outcomes ranging from a merger to a distant passage, depending on the adopted motions, masses, and influence of nearby galaxies. What remains robust is that bound local structures do not simply join the general expansion. Could dark energy eventually rip apart galaxies, planets, or atoms? That extreme future, called a Big Rip, requires a form of dark energy whose density increases in a particular way. It is not the prediction of a true cosmological constant and is not established by current evidence. If dark energy evolves, the ultimate fate must be recalculated from future measurements. Now return to the title question one final time. The universe is expanding, but into what? Within standard general relativity, the answer is, it does not need to expand into anything. Cosmic expansion is the time evolution of the large-scale metric, increasing distances between co-moving, unbound regions. The model has no physical outer surface, advancing through a surrounding emptiness. The observable universe has a horizon, but that is a limit on information, not a confirmed edge of space. The complete universe may be infinite or finite and unbounded, and its global topology remains unknown. A larger external reality or extra dimensions are not ruled out in an absolute philosophical sense, but they are not required by the observations and have not been confirmed. So the phrase outside the universe may refer to three different things. It can mean beyond our observable horizon, where more ordinary universe probably exists. It can mean beyond the total spatial manifold described by cosmology, which current theory does not define as a location. Or it can mean a speculative larger framework, which remains untested. Separating those meanings resolves much of the confusion. We began with an image of a balloon swelling into a room. The universe asks us to remove the room. What remains is not a ball flying outward, but a changing geometry, a cosmos whose distances grow from within, whose visible horizon is not its boundary, and whose complete extent may remain forever beyond observation. That uncertainty is not a failure of science. It is a precise border between measurement and imagination. Thank you for spending this time with Beyond the Surface Cosmos. If this documentary changed the way you picture the universe, please like the video, subscribe to the channel, and share it with someone who also loves exploring the mysteries beyond our world. Your support helps us continue making careful, meaningful space documentaries. The universe is expanding, and the most profound possibility may be that it doesn't need anywhere else to go. Thank you so much for spending your time with Beyond the Surface. Your support truly means a lot to us. If this documentary inspired your curiosity, please like the video, subscribe to the channel, and share it with someone who also loves exploring the mysteries of the universe. Every like, comment, and share helps us continue creating more meaningful space documentaries for you.